I might give a quick background about me. I've moved to London almost 12 years ago now, 12 years next month, not that I'm counting. And I moved into finance because finance is very large there, and for the last 5 or 6 years I've been working in high frequency trading. And 4 years ago I was lucky enough to develop a high frequency trading system from scratch, and that ran for a couple of years before I left. And since then I've been working a lot on my blog and also developing some open source libraries which are not only useful in high frequency trading, but also if you want to change the performance characteristics of your application. So one of the areas that have more recently piqued my interest is the area of using shared memory. And I have a library which does this already called Chronicle, and what that does is it allows you to write out messages at extremely high rate, between 5 and 20 million messages a second from a single thread, and consume those messages in other processes. So you can have effectively a queue that writes everything, logs everything, and does it in sub-microsecond timings. So using a similar concept to this, I've then gone on to develop using thread-safe constructs. Normally you would use thread-safe constructs which are on the heap, but unfortunately these can't be shared between processes, not efficiently anyway. But what you can do is you can use a class called unsafe, which is going to be replaced in Java 9 with something that hasn't been defined yet, but basically there's a class called unsafe which allows you to do all the things in Java you're not supposed to be able to do, including things such as accessing memory directly just by using addresses and pointers and all that sort of stuff. And this can be particularly useful if you want complete control over your memory accesses, but still want to write it in Java and not have to use any JNI. Now the nice thing about unsafe is that many of the methods get treated as what's called intrinsics. So if you look superficially at the code, it says they're native methods, but in reality the JVM optimizes those methods away and turns them into machine code instructions. So they're more efficient than you can achieve by making JNI calls. They also support a number of things such as memory barriers, volatile access, and compare and swap operations. And interestingly, in Java 8, one of the features that was on my list is discrete memory barriers, but that's a bit more obscure, I think. So why use off-heap at all? Well, the main benefit of using off-heap is that is to minimize your GC impact. So, for example, I've tested a hashmap which I've written and will be for general release this week, that supports 100 gigabytes of data. So in this case it was 2.5 billion entries, and it was able to both create this map and then update it 12 times in 12 different threads, and not trigger a GC even with a heap of only 32 megabytes. So there's absolutely, well, the GC impact is minimal. It's like the amount of heap it uses is in a few megabytes, and the nice thing about this is that you can store enormous amounts of data and not need to worry about, well, what will happen to my my GC timings. Now in the past what you would have had to have done is you'd have to have some sort of database to do this for you, and maybe the database would be written in C or C++, and maybe you'd be talking to it via TCP, but unfortunately TCP has pretty fixed overhead, and its overhead is significantly higher than having an embedded database or an embedded store. And so it's very nice to be able to have a store which is accessed directly from Java, so you don't need to go through all these layers of abstraction. Also the memory overhead is quite a lot less because you've got complete control over its layout, and for small key value entries it uses between 1/3 and 1/5 of the memory for the same data, which is quite nice. And the typical read-write latency is below a microsecond. So this is, you can have multiple processes all accessing this shared map concurrently, and the access times are below a microsecond typically. Obviously a lot of these things would be impossible with normal Java code. You wouldn't be able to share data between processes this way. You wouldn't be able to create thread-safe structures that can be shared between processes, and you wouldn't be able to control the layout or when data was recycled. And you wouldn't be able to reduce the header size. So for example, if you've got data that's very close to the size of a header, which is 16 bytes on most JVMs these days, then you've guaranteed a certain amount of overhead. So this didn't quite come out right, but I think it's got all the important information. So here's the comparison between concurrent hashmap and shared hashmap. And it actually has quite a few similarities in terms of the design. Some of the main differences include things such as the concurrent hashmap is of course entirely on the heap, and whereas shared hashmap, it's well under 1%, and obviously the bigger the hashmap, the less it is, so it can be well under 0.1%. Typically it uses concurrent hashmap, it defaults to 16 segments, but I found with shared hashmap you actually want a lot more segments. I'm not sure whether that's why that is exactly, but the optimal seems to be about 1,000, which is quite a bit higher. The next one is important, is the overhead per entry is substantially lower. The reason why there's a range there is that the 120 is if you have a 32-bit references, but as you increase your heap size, you have to switch to 64-bit references. And at this point, the overhead increases to 220 bytes. Whereas with shared hashmap, the overhead is only 25 bytes, and looking at techniques for reducing that further. The pause time can be in the range of about 1 second for every 10 million entries. Now again, if you've got well under 10 million entries, this isn't an issue for you, but if you do have tens of millions of entries, then you're adding seconds to your GC time over and above everything else your application is trying to do. Whereas shared hashmap doesn't impact the GC at all. The other thing that's quite nice is it's persisted to disk. So all of the changes you make to this shared hashmap, because it's memory mapped, all of this gets persisted to your file system, and so when you restart your application, you can restart it very quickly. And obviously this is a concern as your hashmap gets bigger and bigger and bigger. If you start to get into the tens of millions, hundreds of millions, or even billions of entries, you don't want to be reloading them. If your system goes down, you have to bring it back up again. It can take you many minutes, if not hours, to load it off another data source or resync it again if you're starting from scratch. Whereas obviously the nice thing about memory map files is that mapping it back in again takes in the order of about 10 milliseconds, regardless of the size, pretty much regardless of the size. So your startup time issue is significantly improved. The other thing that's interesting is it's not only concurrent across threads, but across processes. Here's another comparison that's kind of similar. Probably the most significant one here is for 250 million entries, 250 million. The worst case latency for concurrent hashmap is in the order of about 17 seconds. Depends on the machine, but in this case it was 17. I've seen it go up to about 42 on other machines. Whereas the worst case for shared hashmap, and consider this is doing persistence to disk, was 160 microseconds, although the typical was about 0.3 microseconds for this test. And even though the throughput is substantially lower for shared hashmap, it's about a quarter of concurrent hashmap, you can see that concurrent hashmap obviously doesn't have any option for persistence. Also, because the overhead is much lower, you can go to much more keys for the same amount of memory. Concurrent hashmap pretty much died with ever-increasing GC times at about 400 million, whereas the same machine running, this is a 32 megabyte heap, could achieve 2.5 billion entries. Okay. Any questions?
Anyway,
Yes.
if you, I've been doing some embedded programming with embedded JVMs, and
Right.
they're as horribly slow, ugly things to work with.
Yes.
Is there a way to use this to speed up slow, dumb, embedded Java?
Potentially, but it depends on the JVM. Not all JVMs treat these methods as intrinsics. So, for example, I know Dvorak doesn't, which would be an obvious embedded system. So you really need to check the JVM as to whether it does it. I know that Oracle and Hotspot do, and I'm not sure whether the JME version does or not.
Well, yeah, I'm lucky I can do the JSE version.
Well, if you can do the JSE version, then you may see a benefit because you have much more control over your memory layout. And the thing to remember is this sort of programming takes a lot more effort, and you have to think about it a lot harder, and there's a lot more work around it. But it may be that that you have a small set of data that's relatively large compared to the rest of the application, and it's worth sort of micro-tuning that data, how that data is dealt with. So yes, I can imagine it would make a difference. Yeah. Sorry. Yeah.
Got a couple of questions.
Sure.
Does this all work on Java 1.6?
This works on Java. Chronicle works on Java 1.6. This one only works on Java 7 at the moment.
And the synchronization between processes on the same machine but not across machines?
At the moment, yes, though there is plan to support both TCP and UDP replication. Chronicle supports TCP replication at the moment.
Right, and I was going to ask a follow-on question. How is the synchronization achieved at the moment between processes on the same machine?
Okay, so there isn't any need. Basically, it's done entirely in the hardware. So what it does is with the memory mapping, when you memory map a file in Java, it actually maps the same physical memory into two processes at the same time.
Standard Unix map.
Yep, that's right. It's what it's actually using under the bonnet. And the nice thing about that is then the only synchronization that goes on is the cache coherency between the level 2 caches. So it's entirely in the CPU. The OS isn't involved. There's no thread involved doing the synchronization. It's as low level and as fast as you can get in current architectures.
Here the other thing is in your memory, but what happens if there's a crash or anything like that? Is there a backup mechanism is running in that?
Sorry, what was that?
Here all the data is generating, it's basically in your memory.
Yes.
What happens if there's a crash or anything like that? It's going to back up or?
Okay, well if the application crashes, then there's no problem. It'll still get persisted to disk because the application's not responsible for this. However, if the OS crashes, and so you get a power loss, then you can lose data. And then that's where you've got to make your tuning decisions as to how much data you're willing to lose. Now, obviously, the way around this is to use replication. And so once you set up replication, you can guarantee that it will be on a certain number of boxes. And then all those boxes have to fail simultaneously for you to actually lose any data. What Chronicle does is it goes further and allows you to control certain operations and say, look, this operation, I need it to go to disk and don't continue until it has. But that's rarely used. It's an option that I've never seen any of my clients use yet. Because generally they just want to go as fast as possible.
So is this a kind of another workaround for a database, or is a?
Yes, it's creeping more and more into the NoSQL database sphere, and it will, over time, it will have more and more of the functionality of something like Redis. The main advantage it has over Redis is that it doesn't have to communicate via some transport protocol, and it persists, whereas Redis doesn't. So it has some advantages over Redis, but Redis does a lot of other things which we haven't even considered.
That's the hashmap.
It's depends on the size. If you've got a small hashmap, then you're better off sticking with hashmap. If you need it to persist, then obviously hashmap doesn't persist. So, but as you get bigger and bigger, once you get into sort of like 50 million plus entries, it really makes a difference. So, for example, one of Yes, basically, if you spend increasing the amount of time GCing, you spend less and less time actually doing anything useful, and that really slows you down. The other thing that you find is that as you get more and more keys, at around 2 billion, you haven't got enough unique hash codes anymore, because there's only 4 billion possible 32-bit hash codes. So one of the things it does is it uses 64-bit hash codes. So it scales a lot better. Its performance, between having 10 million entries and 2.5 billion entries, it drops by 10% in terms of performance. So there's very little drop off, whereas pretty much all the other ones will drop off dramatically.
So what's the typical use case for this kind of?
Typical use case for this is when you've got a large number of securities and you need to update all the prices. So, and the reason why you would use this over, say, Chronicle, which records everything, is that sometimes you don't want every event, you just want the latest event in your calculations. If your calculations are slowing down, or you've got some sort of slow consumer like a client, so if you've got a GUI client, you just want to poll, give me all the latest values every 50 milliseconds or something. Right? So it doesn't matter what rate the messages are coming in, every 50 milliseconds you just go through and give them all the latest values and send them to the client. And if the client's slow, then it may take a bit longer before it goes around again and does the next poll. So it's useful in particular when you've got systems where it is actually a gain to have intermediate updates dropped, so that you're just only dealing with the latest every time. Yes.
Would it be suitable for use in things like data caching engines and stuff, things like Terracotta and that sort of stuff?
Yes, it's substantially faster than Terracotta, which is probably its main advantage, and it has lower overhead. So for the amount of memory you have, you can get a lot more data in there. It also, so for example, Terracotta, usually if you can get sub-milliseconds, you're doing quite well, whereas this one you expect to get sub-microseconds, so it gives you quite an interesting comparison there. In terms of throughputs, they're not quite so different. Terracotta can get good throughput. Usually that's using every thread on every box you've got simultaneously, then you get good throughput. Whereas with this, you'll get in the order of 3 million updates a second in just one thread, right? Which is quite different. So it is also designed to have a relatively small number of threads just go really fast. And that's more the target market, because generally, certainly in high frequency trading, what you want is low latency. You don't often have actually very high throughputs. For example, the FX market, you wouldn't get more than 300 messages a second. That's pretty much the peak rate. But you need to have response times of less than 100 microseconds, pretty much guaranteed. So you've got that sort of issue. Another area it's used is for caching Opera feed. Opera feed, again, you're actually looking at your average rate might be, say, 120,000 a second, which is obviously a lot higher. But again, it's how quickly you can respond to those messages that matters, rather than dealing with even higher throughputs. And so that's one of the things that's interesting. Unlike a lot of database products, they talk about throughput, and maybe they mention latency, but usually the latencies they're talking about are well into the write latency of maybe tens of milliseconds. And if your entire budget, you need to respond in 0.1 milliseconds for everything you do, tens of milliseconds isn't going to cut it. It is that you can start to deal with things much more freely. This one hasn't had enough, I haven't seen clients use it so much, but in Chronicle, the main benefit I have is that you can turn on all your logging. And so you can have all your debug logging, everything's on, and it's still not having any significant performance impact on your system. Where you tend to run in problems with Chronicle is that because it records so much, it tends to use more disk space than people are used to, and so they have to resize their disk requirements. But the thing is that depending on how your organization's structured, disk space can be cheap. So certainly retail price for disk space is cheap. Larger organizations find ways of making it really expensive, but if you've got an organisation where they can make this space as cheap as it is, in the market, then it's not an issue. So recording a terabyte a day is not an issue, and certainly with Chronicle, that's very easy. You can record a terabyte in 30 minutes data. So, and I imagine that's what's going to happen with shared hashmap. Some of the things people will avoid doing because it was just so slow, they can now do. They can record everything. They can put counters all over the place for all sorts of things. And the performance impact is so low that they don't worry about it so much. So it gives you a much freer design decision. And putting in a very large number of keys is no longer such an issue.
So everything, questions?
Okay.
Do you have a shared array list?
I do have an array list, but it's not shared. It's an off-heap one, but certainly that's possible. You can cheat. You can have integer keys, for example, but that won't shuffle down, for example, if that's what you have in mind.
All right, so give me a hand thanking Peter.